I'm MBZUAI from POSTECH. It's my pleasure to serve as a session chair for this session. So first of all, thank you for joining us at this meaningful event. In this session, we will explore the theme of physical AI for real-world autonomy, featuring insightful presentation by researchers participating in the National AI Research Lab. So this session is also being broadcasted live on the official website of the Global AI Frontiers Symposium 2025. Okay, for the second presentation, the Professor Jongmin Lee from Yonsei University will give a talk titled Partially Equivariant Reinforcement Learning in a Symmetry Breaking Environment. So please welcome Professor Jongmin Lee with the big hands.
Right, hello everyone. Thank you for having me at Global AI Frontier Symposium today. And yeah, today I'm going to talk about partially equivariant reinforcement learning in symmetry breaking environment. And this is a joint work with Hyunjung and Minoo and from Yonsei University, and Suha and Roberto from UC Berkeley, and Jongmin from Yonsei University. So these days we have seen that the reinforcement learning has shown great successes, but the core challenge of reinforcement learning is sample efficiency. So standard reinforcement learning often needs millions of environment interactions, which is simply impractical for real-world robotics. Why? Because collecting data with physical hardware is very much slow and expensive and causes wear and tear, right? So for robotics, data efficient learning isn't just a nice to have, but it is an absolute must to have. So how do we improve sample efficiency? So the most effective way might be to use a strong inductive bias, the embedding our prior knowledge directly into the model's architecture. And in robotics, one of the most powerful and the intuitive biases might be symmetry. So think about it. The physics of grasping this mug doesn't change when you rotate the task by 30 degrees or minus 30 degrees or so on. So the relationship between gripper and the target stays the same. But a standard model doesn't know this. It must relearn the same graphs from every orientation. But if a neural network could understand symmetry, it could learn the skill once and generalize it instantly to all rotations. That is the essence of an equivariant network. Okay, so what is an equivariant network? Let's compare. First, a standard network to represent the policy that maps from state to action. We will denote it as a pi n. And let's give it a state S as an input. Then it can learn action A for this specific view. But let's consider the case we give it a rotated state it hasn't seen during training. It is a new input. Then the neural network outputs an unpredictable action. So that means it cannot graph the cup correctly. So that is, if we use the standard MLP for policy network, it must relearn everything for this unseen orientation. This causes sample inefficiency. Now, compare that to an equivariant network. So just like before, if you give it a state S, it learns the correct action A. But here's the magic. When you give it a new, unseen, rotated state, the network's specialized architecture guarantees that the output will be the correspondingly rotated action. So no guessing, no relearning. It learns one version, and it generalizes for free to all symmetric versions. So this provides a huge data efficiency advantage. And this actually works incredibly well when symmetry holds. So look at this the quantitative result on the right side. The blue line the equivariant SAC takes almost solves the task almost instantly, right? Or however, the other method fail completely, or they just slow to learn within a short period of time. So why? The network's internal representation is guaranteed to rotate with the input space. So this enables learning complex skills like this block pushing by generalizing experiences. So it looks perfect, right? When the task is symmetric, it's often the only solution, but there's a catch here. The catch is this relies on the environment being perfectly symmetric. However, in many real-world scenarios, this symmetry is broken easily. So in many situations, constraints are unavoidable. So for example, unreachability. So robots' physical limit breaks symmetry. And sometimes if there is some fixed obstacles, then obstacles don't rotate with the task, right? And also, there might be some singularities or the joint limits. The robot arm itself isn't symmetric. So due to these symmetric breaking situations, this kind of beautiful mathematical idea is a massive real-world wall. So what happens if we ignore this breaking and use a strict equivariant network? So the core issue is even a single local breaking factor has a global impact. So that is an issue here. So let's look at this animation. On the left, we have a perfectly symmetric world. When you rotate it, the agent, goal, and policy will all rotate together. So if you learn an optimal policy for a specific orientation, then it can be easily generalized to unseen the rotation, right? But here, we've added one fixed obstacle here. Now, when you rotate the agent and goal, then that obstacle stays put there, right? The symmetry is locally broken. So in this situation, if the agent goes upside, then it cannot reach to the goal state, right? So there must be some symmetric breaking here. Okay, so, and also, this small and local breaking doesn't just cause a small local error, but this error propagates across the entire state space every time the Bellman backup runs. So that is, in reinforcement learning, this local error propagates globally via Bellman backup updates, poisoning the value function. So the result, some corrupted value function leads to a completely broken and suboptimal policy. So if you look at the red arrows here, so for example here, the agent tries to go towards the obstacle, right? So that means it cannot reach the goal state. So yeah, this is why strict equivariant method often fails dramatically. So how have others tried to fix this? So the most prior works relax the constraint globally, making the entire network less strict everywhere. So first method is so-called residual pathway method. So they just add a standard MLP in parallel to the equivariant network to correct errors, and their outputs are just added. Very simple. Or another way is so-called relax the equivariant network. So they just modify the equivariant layer itself to be more flexible, relaxing its mathematical rules. But that means it cannot fully use the symmetry because of their relaxation. So the problem is both methods relax symmetry everywhere, even where the symmetry holds. So this dilutes the benefits, losing sample efficiency. So our question is, can you do better? can you keep strictness where it works and turn it off only when it breaks? So our key idea is very simple. Instead of relaxing equivariance everywhere, we selectively switch between two models: the efficient blue one, which is an equivalent model, and the non-equivalent model, so the very flexible red one. So we want the best of both worlds, use the blue model where symmetry holds, and switch to the red only where symmetry breaks. So to formalize, we define a new MDP, the MH, called the partially group invariant MDP, with the learned gate function lambda here. The lambda takes state and action, and it outputs either 0 or 1. So, and this gate acts as a soft switch that mixes the two words. So the equivariant components are E or PE, the real function and the transition function. So conceptually, these represent the ideal symmetric words, formally defined by averaging the real words and transitions over all possible the group transformations. And the standard non-equivariant components, Rn and Pn, the standard real function without any symmetry, standard transition function without any symmetry. So the reward and transition becomes the simple weighted mixture, like this. Rh is given by 1 minus lambda times Re plus lambda times Rn, and similarly for the transition. So ideally, if lambda is given by 1, where the symmetry is broken, and the lambda will be 0 where the symmetry holds. So why is this sound? So this proposition shows that the error between our solution, the QH, and the true optimal, the QN, is bounded by the local symmetry breaking. And multiplied by 1 minus lambda here. So when lambda equals 1, that means we correctly detect the breaking, then that term vanishes, no error contribution. When lambda equals 0, the local error is already small. So the lambda effectively the zero out the impact of symmetry breaking, while preserving the data efficiency of equivariance wherever it still applies. Okay, so now that we understand the idea, the next question is, how do we actually learn this gate lambda in practice? So actually, the idea is very simple. Idea is very simple. We train two dynamics model in parallel using the same replay buffer data. The equivalent model, PE, denoted by PE here, and which is forced to follow the assumed symmetry, and the standard MLP, the PN, denoted by the red color, and which is fully flexible with no symmetry constraint. So for each sample SNA, the both model predicts the next state. The PE predicts SE prime, PN predicts SN prime, and if symmetry holds at the specific state and action, their prediction will align, right? Leading to small disagreement. If symmetry is broken at some specific state and action, then PE, the equivalent network, makes a wrong prediction due to some violated assumption, while PN can still learn the true next state, which leads to a large disagreement. So we then treat these large disagreements as symmetry breaking signals. The gate function lambda is trained to output 1 where disagreement is large and output 0 otherwise. So the disagreement between these two models becomes a clean data-driven proxy for detecting symmetry breaking regions. Okay, so now that we can learn lambda, let's see how it's actually used inside the policy and cube function. So how do we use the learned lambda? So it acts as a dynamic switch for both the Q function and policy. So the Q function is a mixture of the QE, the implemented by the equivalent network, and the QN implemented by the just standard MLP. So it is just a mixture, and it is combined by the learned gate function lambda. Similarly, the policy pi blends the equivariant and the standard pi n using a related gate lambda signal. Then we just plug this gate Q pi into standard QN or subject creating laws, the standard reinforcement learning algorithms. The networks inherently adapt, exploiting the symmetry when beneficial, ignoring it when harmful. So yeah, we can practically implement it in a very simple way. So let's go to the experiment. So our first experiment uses the classic grid-word environment. So it is simple, but it allows us to very clearly control and analyze the effect of symmetric breaking. So 15 by 50 grid world, and we will adjust the number of obstacles from 0 to 40. And here is the result. So with 0 obstacles, ours matches the equivariant, the orange one. Ours is the red one. Matches the equivariant network performance, both much faster than the baseline. So the green one is just non-equivariant baselines. And as we increase the obstacles, the strict equivariant network, the orange one, struggles to learn a good policy because of the breaking their assumption. In contrast, ours can still learn very fast, robustly.
Jongmin, could you wrap it up in 1 minute?
Okay. So, and also, we also performed the experiments on the continuous control, the locomotion task and manipulation task, where there are some symmetry, but there are some the symmetry breaking factors. And the result is, yeah, ours is robust and perform very well, but the equivalent network sometimes fail to learn a good policy asymptotically because of the broken the assumption. And this is the qualitative result. So ours, successfully reached the target orientation, but the strictly equivalent RL or relaxed version, they sometimes fail to reach the target orientation. So yeah, this is the summary. So we proposed the partially equivalent reinforcement learning algorithm. So we want to preserve the sample efficiency of the equivalent network, and at the same time, we want to relax the equivalent network assumption, especially for the symmetric breaking region only. So we analyze how the symmetric breaking propagates into the global error, and then we proposed the principal framework and practical algorithms. So the selective symmetry, we are doing a best of both worlds. That's it. Thank you.
So due to lack of time, so let's move on to the next speaker. So let's thank the speaker again for the interesting talk. Okay, the third speaker in this session is Professor Hyunjung Shim from KAIST, giving a talk titled Advancing Robust 3D Perception for General Purpose Robotics. So please welcome Hyunjung with big hands.
Hello, everyone. Good afternoon, and thank you for introduce me. So it is my great pleasure to actually share our recent progresses in the National AI Lab. So since our talk is only 15 minutes, but I have a lot of slides, so I would stay very in high level, okay? So just tell you what I have done in high level. Okay, so the problem that I'm focusing on, we are in 2025, we work on AI, right? And we witnesses all the great progresses that have been made in, foundation models. We all know that nowadays the foundation model can perform very well in the general perception task, and also it can specialized foundation models such as SAM can give us a very fine detail mask like this. Also, like GPT and other, VLLM, those are giving us good answers when we are asking questions from the images. So what else we are having as a problem nowadays? What I want to say is that we are still far beyond in terms of handling the real world. So I want to tell you that, well, nowadays we have made a great progress, but they are mostly staying in the kind of semantic world. So here we are kind of dealing with all those high quality, clean data during training, and also even during this inference testing stage, we assume something, like we are given a nice looking images, the objects are placed near the center and so on. But in reality, it isn't the case. We have to handle the noise data, and it has always an imbalance issue. And sometimes the data is actually perturbed in terms of, for example, adverse weather out there. And also, we always use image data, but in reality, we human also use a lot of sensory inputs as well, right? So, and in practice, when you go outside, we always use the sensory data, but we haven't really discussed those sensory data, how we deal with this, right? And so I thought that is kind of remaining issue. And also, we always use the well-defined definitions. For example, objects. It's well-defined, right? But in reality, especially when you handle this robotics, we have to handle all those part information as well. So how do we define handles? How do we define our neck? Those specific regions are kind of vague and ambiguous, but we still need to define it. So those are, I think, is some remaining issue we have to handle when we go outside real world. So in this talk, I would like to share some of our progress in two aspects. So first is how we handle the perturbations for the robust perception. So here are the things like, okay. So for example, we first talk about how we handle the adverse weather, okay, in LiDAR perceptions. And especially, given by those of adverse weather conditions, we often see the huge performance degradations in LiDAR perception. So we are about to handle this. And another focus is that, we want to define some ambiguous part information as well. And why we need this, I already told you, right? So when we do use a robot ask the robot to perform something, we got to ask to, for example, move the objects. We need to first identify where to grab, right? So in order to do that, we need to define the part information, such as handle. So what else then the real issues here? Okay, I will gonna go step by step, and I will make sure I'm not going over the time. Okay, so first thing, adverse weather. So why is that the issue? Well, it degrades the performance hugely, okay? So what else then people have done so far? Well, people usually simulate the weather conditions. It sounds quite tough because usually, severity of weather is really, imagine like a heavy rain versus light rain, okay? It's very different, right? So, but we got to simulate all those different levels when we want to really use the simulation-based methods. So it takes a lot of time, effort, and often it's hard to really, change those levels. So our question was that, well, is there any other simple way to handle this weather? So for example, maybe we can learn some kind of new data augmentation policy that can mimic this adverse weather, okay, instead of really modeling this physical world. I think it will be easier to do that. Then we don't need to do the weather simulations. So we looked for the literature and found that there are several different types of data perturbations. So we thought that, okay, so those are the kind of starting points. Let's say point drop, occlusions, geometric perturbation, and those are the kind of initial starting point, and we kind of want to look at how that affects the performance of really the LiDAR-based perception models. So we choose actually segmentation model, And then we try to perform some kind of toy experiments and see how those perturbations degrade the performance of our perception models. And we found that actually there are only 3 factors that really affects the performance. Since other factors may not really significant, so why bother to model it, right? So we focus on the factor that really degrade the model performance. And those are the 3 we have been selecting. And then so here is the idea, basically. So we choose the 3 target degradation factors. And then from there, we try to learn a new data augmentation policies in a way that degrade the perception model severely. Okay? So we intentionally create this new data augmentation policy that degrades the perception models. And then once we find this policy parameters, then we fix it, and then use it as a new data augmentation policies to train our model. As a result, so let me push, okay. As a result, we found that actually it gives us a huge benefit in terms of performance. And now you see, compared to the baseline model, you see those plus factor. Actually, these gains were kind of huge compared to the previous progress. So we kind of ourselves was very surprised, and yeah, it seems like augmentation works instead of simulations. And yeah, and also another thing we found is that our method were, in terms of performance, gives us a huge benefit. Especially, we can perform even comparable, even if the other people use the adverse weather data. So that was kind of new finding. Yeah, so these are qualitative. So I just want to tell you that data-centric approaches is valid in this domain of modeling and mimicking these adverse weather conditions in LiDAR perceptions. So it can be a good direction to pursue. Okay, and then one other small actually, I want to also tell you that in this LiDAR perceptions, we often kind of lose one thing, meaning that people always look at the average accuracy. Okay, average accuracy means a lot. That's what people think. But we've kind of found the interesting results. That is, why do we need to recognize the objects in LiDAR perception that usually consider autonomous driving application, right? So why do we do that? Well, we want to go faster and safely, right? But then in terms of safety, we need to take care of those things that move around instead of static scene, right? But what we found is that in this LiDAR perceptions, high performance is achieved in stuff objects, which doesn't move. For example, building, for example, rod. Those are the things that doesn't move. Of course, it's important information, but what I'm saying is it doesn't move, okay? But human, vehicle, trucks, those are the objects that moves around, right? And very interestingly, the existing studies shows a huge gap between stuff and things classes. And we kind of pointed out this is not right directions, okay? We have to make sure that things class should have a good performance as at least comparable to stuff class. Okay? And we kind of tracked these performance regions and found that maybe, stuff class has more pixels in training, so we better learn the stuff classes. Compared to that, things class has a less number of pixels, maybe that is the regions. But still, we need to figure it out. We need to solve this problem. We need to get the good performance for things class so that we can at least take care of those moving objects carefully. And that will be important for autonomous driving scenarios. So yeah, that's basically the starting point. We kind of find that, okay, things class performance is not as good as stuff class. We want to actually improve that things class performance. How can you do that? And why is that the case? And we found that actually there are systematic errors that's actually causing things class, misclassify things class as a stuff class. So we often make such a mistake when we run these LiDAR perception models. So the idea is very simple. Although we have another idea, but I will focus on the first idea, okay? So that is, here. So what we found is that, okay, things class is often misclassified as a stuff class. That is a phenomena, that is an issue. So what can you do? So we thought that, good thing is that we know, these classes, for example, vehicle, that's things class. So we want to add an extra supervisions that says, for example, person. Person is person class, but person is things class as well. Okay? Then that can be an extra supervision, right? So it's not a stuff class, but it is a things class. So we are actually putting another extra supervisions here, and then train our model. Actually, this superclass, superclass label is not shown here. Okay, fine. So these superclasses are not just, it's here. So this superclass is course class. So course class means we only assign either stuff or things, but this superclass is something more precise. For example, human class. Human class include a motorcyclist and then a pedestrian and so on. So those are all indicating humans, right? So there are human classes and the vehicle classes and so on. So it's more fine-grained superclass. And you found that the superclass actually gives us a huge benefits, okay? It meant to improve the things class. So those are our progresses in this area. I only have a 2.5, so, okay. So let me just briefly talk about this topic, okay? And the final 2 papers are regarding this open vocabulary part segmentations. Here, why do we need a part? I already gave you the intuition, so I'm not going to repeat it. So, but the issue I want to share you guys is that part is challenging because it's small, diverse than objects, and also it's quite hard to define, okay? So, and let's say, even humans, okay, I make the part, the ground truth labels differently from you guys because everyone has a different, neck information in mind. So some people start the neck from here, some people start the neck from here. So everyone has a somehow different definition. So that's another challenges. But at least a human has a very good way of learning this part informations. For example, at least when I learn the leg information from the horse, I can generalize that idea to detect the leg of, for example, deer, right? So we have that ability. But because this part segmentations, we always make a label like, okay, this is a bird wing, okay, this is a leg of bird, and this is a leg of, say, dog, and we memorize that each of them separately. So the idea of leg, for example, is not really generalized. And so as a result, what happens is that when we recognize an object like this, we will find that sometimes the head is from the dog, but the body is from the cat, but leg is back to the dog. Such a strange creature, right? There's no such a strange creature, right? So we found that, okay, something wrong, right? So our knowledge is not well generalized. And also, we don't really take account that entire extent should belong to the same objects. So those are, I think, the key information I wanted to point out here. So we kind of learned the things like this, okay? So so first thing is that in our methods, we try to learn object as is. And we also learn the part as is, okay? So we try to focus on the part information and object information separately. And then finally, we want to learn that this is the object's part, okay? So for example, as back to the dog thing, okay? I try to learn that this entire object is a dog. And then I try to separately learn the dog, leg informations. And then later on, I try to learn, okay, this is the leg of dog. Okay? So these three information separately, I learn it so that I can have a better idea about legs, dogs, and leg of dogs separately. Okay? So this helps us to generalize our perception on parts as well as on objects. Okay, yeah, these are too much, information, so let me just skip. Okay, so we actually got the very high performance after all, which is a good thing. But then we still found that this part segmentation in terms of performance is very low. You see like this bad, okay, 10, 20, it sounds like very hopeless, right? So we thought maybe there is another bottleneck here. And then we found that actually VLM that we use to recognize the part in a zero-shot manner is actually very weak to understand this part information. Okay, so this is I'm learning out of time. So we have done something, okay? But the thing I wanted to point out here is that, in fact, this additional structural information were very useful to improve the performance as well. So our final work gives us a huge performance improvements to improve these weak signals from the VLM, as well as the lack of understanding in structural informations altogether gives us a huge improvement. So I think nowadays we can actually start this 55, I think is reasonable. I personally think that if our algorithms start to achieve more than half, then we can, we can do distillation, all the things, because at least our perceptions are better than, just random flipping. So I think we have a more chance to improve these results after all. Okay, so far, these are the results. And overall conclusion here is that, I talk about several things, but the thing I want to tell you is that, we need to push forward to have a robust perceptions, okay? And then we still have remaining issues, how to handle the real sensory data, such as LiDAR and extra. And also, we need to use, we need to find more generalized methodologies to handle such ambiguous and not well-defined data as well. So far, that's it. Sorry for the late, and hopefully
okay, let's thank the speaker again for a nice talk. Okay, let's move on to the next talk. Okay, the first presenter of this session is Professor Sungjoon Choi from Korea University, who's going to be talking about the presentation titled Towards Reasoning in Vision Language Action Models. So please welcome Professor Sungjoon Choi with a big round of applause.
Good afternoon. My name is Sungjoon, and today I'll talk about toward reasoning in robot foundation model. And you got to see there's a question mark at the end. So it's not about our recent work on reasoning, but also do we really need reasoning in robot foundation model? So I try to give you some questions and try to define some terminology myself. A little bit of my introduction, but due to the limit of time, I'll just move on. So last week there was an ICCV, and I was in Hawaii, and I had some debate with my colleague about the generalization. So the thing is, a lot of people think generalization as of the buzzword, saying that we can achieve everything, especially when it comes to a foundation model. They try to argue that we may be able to solve all the robotic problem if we have enough data set. So I think I decided to add this terminology slide because I really like this quote. Language is source of misunderstanding. I really wanted to highlight some of the terminologies that we all often used without any consensus. I think the first one is the physical intelligence, right? I mean, the physical intelligence, the term, as far as I know, was originally talked by Sung-baek Kim MIT in 2020, which was trying to meant unconscious human movement with a lot of contact and a lot of interactions. But nowadays, if you think about physical AI, we often think about this by sentient men, right? And we think about any human eyes moving inside our house, try to solve everything. So that's one thing that I like to point out. We often think about generalization overfitting, so meaning that the generalization that I used to learn back in my machine learning days is that the discrepancies of the performance between training set and test set in which they are drawn from the same distribution with IID manner. However, nowadays people kind of think that general adjustment, again, is like an AGI. Overfitting originally mean that it is a performance gap on the test set, but nowadays people tend to say something like, we are trying to solve one specific problem, so it's overfitted. So it's, again, not the overfitting that I have in my mind in robotics. Reasoning, again, reasoning, a lot of people think reasoning in terms of the reasoning LLM, but there's a big gap between the LLM's reasoning and VLA's reasoning. What I mean by that is if you think about LLM, it's autoregressive, meaning that we can kind of reason based upon our previous statements. We can think on and on, like inner monologue. If you think about robotics, I mean, if you can speed out actions, but we don't really know the consequences of action because we don't have a word model. So the lack of the word model makes it this reasoning in a visual language action model really different from those of the LLM. If you look at like a Momo Act, for example, from the LLM Institute, they do something like verbal and visual reasoning, meaning that they try to explain what they're trying to do in terms of the verbal sense. And by conditioning on the verbal, they try to argue that that is reasoning. But in order to do the real reason, like, for example, like the Monte Carlo tree search, we need a word model. So we need to have some sort of a, way to predict that. But training a world model is often more expensive than training a visual language action model. So it's, again, different words and different perspectives. So I don't have any answer to that. I just point out that there are some discrepancies between the understanding of the terminologies. For example, like a good old-fashioned robotics myself to the learning side of you guys, there's some difference, some misunderstandings. So in terms of that, our lab has been doing some different stuff. So first thing that we do is learning from observation. So what I mean by learning from observation is that we try to get some information from different modalities. For example, if you want robotic motion, all of the video that you see here is work from our lab, maybe this year or last year. So for example, the motion retargeting, if you want to generate robotic motion from human, you got to think about, we got to handle the discrepancies you often call the embodiment gap in visual language action models. So how can you handle that? How can you handle the different proportions? How can you handle different force ranges? If you can able to do that, then you can actually generate robotic motion from text because you have a lot of motion diffusion model that can generate human motion from text. And by having this motion retargeting, we can come up with this motions of G1, even boxing. So we have done that. It can go even further for the quadruped as well. If you have motion capture data for the quadruped, we can do the same thing. It's all the same stuff. All the things about physics. You may have a contact label. You do some optimization based on some equation of motion. You solve some MPC, you solve some RL. You get the end of the day, you get some motion. So you can do some ballistic movement like that. So again, everything is like different modalities. If you have a motion from cat, how can you move it to go on? If you have a motion from YouTube, how can you transfer into the robot, right? Another side of work is dexterous manipulation. I am participating in a company called Real AI and closely working with those companies. All of the work that you see here is a little bit of part of work our lab has been done. So in order to do dexterous manipulation, we need to do teleoperation, right? So that is myself wearing the same shirt. I don't mean that, but anyway, that's myself with a really good robot named Alex. So how can we do that? How can you have that teleoperation with the haptic signals and all this stuff? The thing is, we don't have the model, right? So we don't have the data set. We cannot use learning-based methods. So everything's based on optimizations and traditional robotics manner. By combining all the stuff all together, we were able to do something like tool usage, like opening the bottle, pouring the water. This is available on YouTube, by the way. So you can do all those stuff like opening the bottle and pouring into the cup. You can kind of see what's going to happen. Of course, you can do pick and place. But the thing that I really mentioned over here is that it's not that simple. Right? If we have enough time, I can talk all day about how difficult this problem is and how many pitfalls that you may fall into. What are the limitations of this method? I can go on and on and on. Love to discuss more in the panel talk. But anyway, it's not that simple. It's not that simple as collecting the data set because the thing is, we don't get enough sensor information as humans do. Humans are really great at getting a lot of sensor modalities like, for example, haptics and touch and sounds and vibration, but we don't have that on robots. And how can you handle that? We don't have any data set for a newly developed hardware. How can you handle that as well? So those are the stuff that we have to think about. Again, I don't have any answer. We're just working as we said. We'll move on. So now let's talk about reasoning, which meant to be our original talk. So we've been doing visual language action models ourselves as well. So the main focus of work is that, well, we have this robot. This is in my lab, my students collecting the data set. But the thing is, we often make a lot of mistakes, right? So however we make mistakes. So how can you utilize the data set, like not only positive, but the negative? So our questions start with this simple question. How can you leverage both positive and negative demonstration in VLE models? How can you do that? Actually, the data quality really matters. And the initial work from the PyZero, they mentioned that this sentence, intuitive training only on high quality data does not teach the model to recover from mistakes, but training only on lower quality pre-trained data does not teach the model to act efficiently. So how can you combine those all together? I mean, we can collect both positive and negative data, but just training as it is does not help the performance. So as I said, we start with a simple question, but we end up having, hey, we need a world model to the reasoning. However, we don't have any world model, and we don't have any Cosmos, we don't have any training data, so we don't have any GPU, by the way. So how can you do that? So we kind of try to, go in the middle of so we try to model the scene not on the image level, but on the scene graph level. And we try to predict or train the world model that predicts how the scene graph changes over time, conditioned on the action. So in which the action has been defined by the text. So the JEPA world, that actually has a world action conditioned prediction model, which we did pretty much similar stuff. Of course, based on the planning, we do execution by tree search. So let me give you the results over here. So for example, whenever we're given an initial image, our model can predict how the scene graph changes over time based upon our action. So we do some sort of beam search, we end up getting some tree. And of course, we also train a value function head on top of our system2 function. And then we get some sort of a tree search, like if you know the Monte Carlo tree search, exactly what we do. Also, we do something like that. For example, if you see this real scenario, this is actually the real inference results. You can see that the most successful prediction is move the clock on the left, push the sponge in the cabinet, and close the cabinet. That seems like the most plausible way. So again, this is an initial result that we're working on. We try to submit a paper this month. But anyway, this is our work that we've done. But while we're doing it, we really find out that we need a good world model to do reasoning. But without the world model, well, we don't have any data of the world model. So it's like a chicken and egg problem, so on and on and on. So I'd like to discuss more about it. So I got like 5 minutes. Let me give you the final thoughts. So I call it Allman singularity. He said that intelligence to chip the meter is well within grasp. I totally agree. If you think about GPT-5, it's pretty much cleverer than I do. How about the physical intelligence? Does we have physical intelligence to meter within a grasp? I don't think so. So for that, for the conclusions, I really have a hard time because in front of those distinguished researchers, you guys, I try to lean on authorities of big guys. For example, Rodney Brooks. So Rodney Brooks is one of the pioneers in robotics. He's actually the founder of the iRobot, the Roomba that you know of. He's actually multiple companies. He's a serial entrepreneur. So he mentioned the 3 laws of robotics. The first thing is about the appearance. So the appearance of a robot makes a promise about what it can do, how smart it is. For example, if you think about humanoids, we expect a human robot will think like us and act like us, which is not. The second sentence of the first law is that it needs to deliver or slightly over-deliver on the promise or not be accepted. So it's not, bright future in terms of the Rodney Brooks third law. Well, second law is about safety. Let's keep that. And third law is more practical. It states that every 10 years gets another 9 in reliability, meaning that if you want to go from accuracy of 90 to 99, you need 10 years. 99 to 99.9, you need 10 years. If you think about the performance of VLA is like 80%. So if you want to think about how many years that we need for the VLA model to go up to 99.99, we probably need 40 years. So again, not bright future. But as a roboticist myself, I'm willing to have a bright future. So let's bring up another 3 laws. So this is the Arthur Clarke 3 law, which I like a lot. So the first one is interesting. When a distinguished but elderly scientist, I don't mean to say Rodney Brooks, but states that something is possible, he's almost certainly right. When he states that something is impossible, he's very probably wrong. So we also can think about a bright future as well. Second is very important. The only way to discovering the limit of the possible is to venture a little way past them into impossible, meaning that we got to, work really hard. The last one, any sufficient event technologies distinguished from magic, is something that I really like. It's actually the quote written on my webpage. And this actually goes along with one of the motto of the digital research in which I did the postdoc. It's basically beyond magic. The thing that I really like about this sentence, any sufficiently advanced technology is indistinguishable from magic, is that it kind of highlights not the methodology, but the problem that we are trying to solve. Because when we are thinking of a lot of researchers out there, we try to use methodology, we try to use SSL, we try to use detection, we try to use LLM, and so forth. However, the thing that really matters to people, or the industries, or the technology or science is that the problem that we try to really want to solve. We don't really have to stick to a simple problem. For example, we don't really have to solve physical intelligence using visual language action model. We don't have to solve it using a raw foundation model. So that's something that I want to say. I think I made it within 13 minutes. Having said that, that was my final slide. All the work that have been done by students. I'll be happy to have any questions, and thank you for your attention.
Okay, thank you, Sungjoon, for the interesting presentation. Okay, finally, yeah, we have time for questions. So if you have any questions, so please raise your hand. The microphone will be brought to you. Any? So, okay, I have one question. So in your presentation, so I think there was some statement that emphasizes the reliability of the prediction, especially in the robot actions, right? So when it comes to that issue, so what do you think is we miss in the current state-of-the-art visual language models?
I don't really have the answer to that. I'd like to discuss more. But I've been talking with you the same issues. I think language is a little bit overrated in the physical AI. The reason why I say that is the language is actually the consequences of the action, not the source or the pure description of the action. So if you could remove the language part on the visual language action model, we can actually reduce the model significantly, making the model to train really faster and inference more faster, making a more agile and dexterous movements. So I think we could do more than now if we don't focus on the language modality. And actually a lot of papers states that the language understanding performance of the visual language action models are really bad. So that could be one direction we could go upon.
Okay, thank you for the good answer. Anyone?
I'm very used to having no questions, so I could have another next speaker.
Okay, then let's thank the speaker again, and let's move on to the next speaker. Okay, the next speaker is Professor Suha Kwak from POSTECH, who will be giving a talk titled Robustifying Vision Foundation Models with Gated Rank Adaptation. Please welcome Professor Suha Kwak with big hands again.
Thanks for the introduction. I'm Suha Kwak from POSTECH. And in this talk, I will be talking about our recent work on improving robustness of vision foundation model. And this is joint work with Sohyun and Yeho, the graduate student of GRIP, and Dr. Lucas Hoyer from Google. The title of this session is Physical AI for Real-World Autonomy. And we have seen and heard a lot about the major applications of related to this. Examples include autonomous driving, delivery robots, and manufacturing and collaborative robots. As a computer vision researcher, I'm interested in the role of vision foundation models in the physical AI applications. The video I'm showing here demonstrates the segment anything model, or SAM, which is very well known nowadays, working with the gaze tracking module from an egocentric view. Although this video shows SAM being utilized from a human perspective, it can be applied to physical AI systems also, like robots. For example, through SAM, a robot could segment the region of an arbitrary object at the center of its field of view to gain some clues for interaction and manipulation, or it could identify key objects mentioned in the user's instruction. Since applications of physical AI are generally high-stakes applications, robustness is essential for their practical use. In particular, they need to operate robustly even with degradation of the input visual information, which is, however, quite common in real-world applications due to adverse weather, low light conditions, and blurs in nighttime images, and overexposure in daytime images, etc. But as is well known from many examples, existing vision systems are often not sufficiently robust against input degradation. The image here shows such an example of an accident caused by this lack of robustness. Since our interest is in vision foundation models in this presentation, we looked into whether SAM, the representative vision foundation model, is sufficiently robust against input degradation. As a result, as can be seen here, we found that SAM is very sensitive to even mild image degradation. And the degradation severely damages the segmentation quality. Actually, we are not the first to study the robustness of vision foundation models, since robust SAM was introduced at CBPR last year with the same purpose. Robust SAM is a type of knowledge distillation framework. It involves the SAM model taking corrupted images as input and learning and utilizing the knowledge from the SAM model taking clean images as input as teacher. To this end, robust SAM first prepares clean images and its degraded version by applying existing image corruption functions to the clean images. And then it adds anti-degradation modules to the SAM model that takes degraded input. And train only these modules to improve the robustness while maintaining its generalization capability. Specifically for training, it applies a segmentation loss using the ground truth mask, and also uses representation from the SAM model taking the clean images as the guidance for learning representation that is invariant to diverse input degradation. But this model has two main limitations. First, it requires pairs of clean and degraded images, which cannot typically obtained by usual RGB cameras. So it heavily relies on the synthetic image corruption generator. And it hinders the generalization capability of this model to real-world degradation. And second, since this work aims at learning representation that is invariant to diverse image degradations, it is not adaptive to specific degradation type affecting the input at hand. So it also hinders the performance improvement. So in this work, our goal is also improving robustness of SAM to input degradation. But we prioritize three key aspects. The first one is, of course, parameter efficiency, because the vision foundation models have a lot of parameters, and it is ineffective and impractical to retrain all the parameters from the corrupted images. And second, fine-grained and input-aware robustification to more precisely address the input corruption at hand. And third, training with unpaired real degraded images, so that our training paradigm does not rely on the pairs of clean and corrupted image pairs for training. And our starting point is to introduce lightweight adapters into intermediate layers of frozen SAM. This is mainly for parameter efficiency. And that starting point, I think, may remind you the low-rank adaptation, LoRa. LoRa was originally proposed for efficient fine-tuning of foundation models, and it adds low-rank update matrices to existing parameter matrix of vision foundation model or any foundation model. And importantly, that update matrix is decomposed into two low-rank matrices. And it has several advantages, And I think the most important one is the LoRa is parameter efficient because of its low rank. And also, it does not add any additional inference latency because at inference time, the original wave matrix is merged with the updated matrix we trained separately. So a single wave matrix will exist for each layer. So it does not add any inference latency. And we found that low-rank adaptation offers a promising foundation for overcoming the previously discussed limitations. By introducing and training lightweight adapters within the frozen SAM, LoRa improves the robustness parameter efficiently while preserving its generalization capability. And also, our empirical analysis confirms that SAM incorporating LoRa achieves impressive performance, impressive robustness without using paired clean and degraded images for training, as can be seen here. So it establishes a strong baseline as is. But our analysis also reveals that the fixed rank of the adapter hinders its effective adaptation to a wide variety of image degradations. We found a significant variation in the optimal rank of the adapters for different inputs with different corruptions and content. So, for example, by choosing the best rank per sample, which is kind of oracle and unattainable, but by doing so, we can achieve great performance improvement over the normal LoRa integrations. This underscores the need for input adaptive rank modulation. So motivated by the empirical observations in the previous page, we proposed gated rank adaptation. So the key idea of GARA is dynamic adjustment of effective rank of a LoRa adapter. So first decompose the LoRa wave matrix, update weight matrix into multiple rank 1 components, and dynamically chooses a proper subset of the components according to the input. So by doing so, we can achieve fine-grained and input-aware robustification, unlike the previous naive application of LoRa or robust SAM. And also, it's still parameter efficient, not as parameter efficient as LoRa, but still, the additional parameters and inference latency caused by GARA is marginal compared to those of the original SAM. And also, it allows us to adhere to the standard training protocol because it does not require any paired, clean, and degraded images for training. And it allows us to train the entire model using only the segmentation losses. So GARA adapters are introduced into intermediate layers of the SAM's image encoder, more specifically its query key value projections. Then the adapters are trained with the standard segmentation losses. So unlike robust SAM, it doesn't require paired clean degraded images for distillation. And as can be seen here, each GARA adapter maintains multiple rank 1 components and dynamically chooses a proper subset of the components according to the input. And the modules are trained in an end-to-end manner with only the segmentation losses. More specifically, we design the way of choosing the components by a hierarchical gating framework. Each GARA adapter first coarsely selects between lower and higher rank spaces based on the input. And then within each of the selected rank spaces, each gating module finally determines the rank of the adapter by activating a subset of the rank 1 components appropriate for handling the input. And the coarse rank space selection separates the adapter's components into two exclusive sets tailored to different degraded inputs, demanding different representation capacities to mitigate potential conflicts between the two sets. And the two gating modules are implemented as multi-layer perceptrons, and we adopted the Gumbel Sigma module trick to train these gating modules with loss gradient. We integrate GARA with SAM, and the resulting model is called GARA SAM. which is our final model. And this is compared with the original SAM and its improved version called HQ SAM, as well as robust SAM. And please note that the majority of the benchmarks are synthesized by applying synthetic corruptions to clean images, but BDD 100K, LIS, and HDC are real corrupted data sets. Corrupted images degraded by adverse weather, low light conditions, etc. And GARA-SAM surpassed all the competitors on synthetic corruption benchmarks. But more interesting observation was obtained on the real corruption benchmarks experiment. So it, of course, achieves the best in all settings. And more importantly, it achieved a great improvement if it is fine-tuned on real corruption images, which is impossible for the robust SAM, because robust SAM required paired clean and degraded image pairs. But because GARA-SAM does not require such training data pairs, it can be directly fine-tuned on real degraded images without any clean counterparts. And such fine-tuning on real degraded images improved the performance a lot. Here are some qualitative results. Red stars indicate point prompts, and red boxes represent box prompts. And GARA-SAM produces reliable segmentation masks under severe synthetic corruptions. And it also outperforms the previous work on real-world corruption data sets. In particular, the third one, maybe you cannot see anything, but this is real low-light condition images. And our model finds the mask almost identical to the ground truth in this darker scene. And we also analyze how GARA activates rank-on components for different images with different corruptions and content. So these are the visualization of distributions of activated rank-on components. Even with the same input, GARA-SAM activates different sets of rank-on components depending on different corruption types. Similarly, even with the same corruption type, GARA selects different sets of rank-on components depending on the input content, as desired. So in summary, we propose a new method for improving robustness of vision foundation model, specifically SAM. So it's parameter efficient, and it enables fine-grained and input-aware robustification. And more importantly, it demands no clean degraded input pairs for training. And it achieves outstanding performance on multiple benchmarks. Thank you for your attention.
So we may have time for just one question if you have. Okay, otherwise, let's thank the speaker, Professor Suha, again for the nice presentation. And then the final speaker in this session is Professor Ivan Laptev from UAE MBZUAI. He's going to be talking about the embodied agent from perception to action via world models. So please welcome Professor Ivan Laptev with the big hands.
Can you hear me? Great. So thanks for coming to my talk and the invitation. So I'm going to talk about videos. I've done work on video understanding in the past. I'm still interested in this subject, so let's look at, start with a video. So here's a video of some nice kids who are cleaning the room. So these are not my kids. My kids are usually doing it in a reverse order. So we are, well, what is video understanding anyway? So we are able to do a lot of things nowadays. So this is out of the box, for example, 3D human pose estimation, which works amazingly well nowadays. It's not completely solved, but it works very well. So this is just output from GPT. You don't have to be a vision researcher to produce these results, or Gemini produces amazing just in a few seconds, it produces an amazing description of the video, which was hard to believe that we would get it just a few years back. Right, so are we done with the video understanding? So actually no, so because you remember my kids are not cleaning this room, so I need helper. And so we still don't have these robots which would do things for us, like cooking, home cleaning, and many other things. Right, so what are we missing? We have almost solved all these proxy tasks of computer vision, and still it seems we are quite far from building robots which of course needs this vision and will do useful things. So what is the problem? Well, the problem of course not just home cleaning, so it's more generally it's a basic robotics problem. This is from bringing the world from state A to state B, okay? And there are infinite number of incarnations of this or instantiations of this problem, right? Building, cooking, and so on. So, and this can group this all under the planning. So what actions do we need to perform to bring the world from state A to state B? So this is one problem which we are interested in my lab. And another complementary problem, which Jan also talked about this morning, this is simulation of world models. So what happens if, so we need a model, so say we have a plan, great plan, but then we don't want to maybe execute it because maybe the plan is bad. So we need a model which we can ask, is this actually a good set of actions for this scene or not? So we need a simulator or world model. All right, so I'm going to spend the rest of the time talking about two works which we did recently in this domain. Okay, so in starting with the simulation. So here is a work which we just submitted recently. So learning to generate object interactions with physics-guided video diffusion. So we're interested in, so we are posing the world simulators or world models as a video diffusion model. And okay, let's just get a brief look what video diffusion models can do today. They can do a lot. You know Sora, so these are two other models, Veo and Van. Okay, they do amazing things, just prompted by text. Again, just a few years back, we could not imagine this is possible. But usually, okay, first you see good results, and then these are results which are primed by text, so quite general guidance. So now if we look specifically at object interactions, so the same models, they often fail. So either if you prompt them by text, or specifically there are a few models which actually you can prompt by low-level guidance, like motion direction. So they usually don't work very well. So we try to fix this. And so this is a more, you can say, experimental exploration. But the finding, I think, is interesting. So what we are trying to do is we try to take the diffusion model, video diffusion model, which already was trained on lots of videos. It knows about the variation of the world, visual variability, and so on. And we try to enrich it with some physical knowledge. So how do we do it? Actually, the idea is quite simple. So we take a physics simulator, which is not great in terms of visual variability at all, in terms of shapes or appearance. But in this physics simulator, which is, okay, here is a Blender, but you can do any other, so it can actually simulate quite well simple object interactions. So the idea, can we just bring this knowledge from simulator into the real world? Okay, so what's our data look like? So we generate lots of data with the physics simulator, okay, and we also generate the motion masks, okay. And by the way, so motion masks here, so you see that we generate them for the objects which we try to control. So it's a low-level control by velocity. So mask is generated for the full trajectory of the object, but in the training, actually, we are first training with the full trajectory, and then we remove the full trajectory because at the inference, of course, we don't want to use it. Right? So what is happening at the inference is that we are given the velocity and the point location of an object. So we use, for example, sum to to segment an object, and then this gives us a mask, and that's the input to the video diffusion. So what I didn't mention is that how we train it, so for the lack of time, so basically we take control net, standard control net applied to video diffusion where we control the motion of the target object with a mask, which also describes its velocity. Okay, so what happens here at the inference, I can play it again. So we give the velocity vector. Velocity vector defines the motion mask, and so you see the interaction of object happening. So to give a few more qualitative results, so here, for example, you can give different velocity. So okay, it's the same scene, two TVs, so we can imply different force or initial impulse to the one of the TVs, okay? And so here you see bump. And if you apply more, like larger velocity, so there's more motion happening here. So we found also that apart from the low-level control, it's also quite important to control it on a high level by text. So, and actually, how do we, so say, well, you can imagine you have your own world model in your head, so you can imagine what may happen if you move this vase, if you push this vase from the chair, okay, and how do you know? So, well, you know from experience, but actually the vision language models, they also are quite good if you ask what happens to this vase, so they will tell that it will probably fall down and break apart. So that's what we actually ask. We ask VLM, you know, which one in this case, so what will happen, and provide the high-level guidance. In addition, so of course we use what we've trained from simulators, which provide low-level guidance, motion guidance. So these two things lead us to actually something which is arguably looks physically plausible. So here's another example of a glass which falls from this high chair. And okay, you can argue if this is physically plausible or not. So what we can say at least that this is definitely much more physically plausible than the original model, Cog Video X, which we started with. So if we didn't train anything and we just gave it original text, that's what it gives. Right, we also asked people what they think, comparing our model with some other, well, original Cog Video X, VAN, which is one of the recent models, and force prompting, which is the competitor methods, which is trying to control, low-level control of the video generation by, okay, and so this is for real images, and this is for synthesized images where we predict and measure how well we predict the motion. All right, so I hope that was rather clear. So I want to jump to the second work, which is from simulation to planning. Okay, so this is work done together with called Dupont in Paris. So here the problem is now we want to simulate or animate people interacting with objects in 3D. So assumption is now that we know everything about the environment, the 3D, and we want to put a person there, and we want to say that pick up close stance and put it next to the sofa. Okay, and then we want to animate this. Why is it useful? For many things: character animation, video synthesis, and also what's more to my heart is the robot control. So been recent work, for example, from Berkeley, video mimic, where they retarget the learned motion of people to robots. Right, so let's very quickly look what happened recently on text-guided motion, human motion generation. There are plenty of works. They are working pretty well. We are interested in animating people who manipulate objects. So for this, very important is that we control these characters by motion of hands, for example, or some other. So spatial control is important. So there's been also work recently on spatial control. Okay, so omni-control is a diffusion method. So masked mimic is a more RL method, which is trained in a physics simulator. So now, if we give them these methods sequences like spatial guidance for, say, object interactions, where the hands move by interacting the object here, and I guess this is the case where you move some box on the floor. So this is a diffusion model, so it's produced one type of error. So this is a mask mimic, as I said, so it's trained in a physics simulator, so it's much more physically plausible, but still it cannot follow. So we are trying to fix, based in this work, we are trying to fix this problem. How do we do it? So the observation is that actually the problem is the training data, one of the problems. And so the training data which was used to train these typical models, it's high quality, but it's motion capture data, but it doesn't have much object interactions in it. So there is some small data with object interactions, but it's too small. So the contribution of this work is actually to automatically collect the data with human motion, including object interactions. How is this done? It's collected from internet. So actually the 3D human motion estimation nowadays is very good, not perfect, but quite good. So to be used as an automatic human motion collection on a large scale. So we collect this data and now retraining exactly the same models as before. So we see here mask mimic before on the left and using our new data on the right, so it works much better. Also diffusion models. So different, quite different model, but also works very well. Right, so let's see what we can do with this type of model. So our original goal was to take a 3D scene and the text instruction and produce the animation of a person interacting with objects. So how do you do it? So we are, of course, using now our model, which we have just trained. And so the text, we put text into LLM, text together with 3D description of a scene into LLM. Incredibly, LLMs do understand 3D when they're given the coordinates of everything, and so they are able to generate from this text and the 3D scene. They're able to generate these yellow key points for the motion of the lamp in this case. So this we interpolate by green into trajectories, and then the person here. So it's we ask the person to just follow, the hands of the person are controlled to follow the green trajectories, and that's how we get the animation. So by the way, so you can, okay, it looks reasonably well. It's not perfect with the hands because we are not modeling the hands, right? But the overall motion, so actually it's a mask mimic, so it's physically plausible, so we believe it could be transferred quite easily to the robot. And okay, so also something here is a more complex scenario. So it's a constrained environment where the person is supposed to get something under the table, so it still works well. All right, so I think I'm getting to the end of my talk. So here's a summary. So I talked about two things. One is mask mimic, so take away, surprisingly, so where you take a video generation model, you train control net on a very simple videos from simulator, which focus on object interactions. This knowledge of object interactions gets into the video model. At the same time, the video model doesn't forget about the rest of the world, what it learned before, so you can actually transfer it pretty well. And second work is interposed human motion in web videos, improves models for human motion generation and enables zero-shot animation of object interactions. Okay, I have a few, like 0 seconds left, so this is my last slide. So what I think on the world models, neural simulators, I think that's what interests me most. I think there are very open questions here. How should the model? Should it be a completely latent representation? Or should it be 2D video diffusion? Or maybe it should be 3D video diffusion? So what I think the future, if I were asked this question, I would argue for the last part, because in 3D, so if you would be able to generate both 2D and 3D, so we would be able to impose geometric constraints, physical constraints, many things into diffusion models and hopefully improve them. Thank you.
Okay, let's thank Ivan again for the interesting presentation. Note that this is not the end of the session, actually. We are moving on to the panel discussion session. So first of all, I'd like to thank all the 6 speakers for the excellent presentation. So we'll move on to the panel discussion. So this discussion will feature the 6 speakers who already have presented, along with Mr. Yong-Soo Kim, the head of AI Convergence R&D Labs at POSTECH Holdings. So may I kindly invite you, all the panelists to come up to the stage. And please join me in welcoming all of them with a big hands. Yeah, I mean, the stage is quite cozy, so anyway. So actually, this panel discussion is the shortest panel discussion I ever have seen before. So this is just, we have 30 minutes, because next session will be starting like in 40 minutes. Okay, let's get started. And this panel discussion is, as you know, is titled like Physical AI for Real-World Autonomy. And it's my, of course, pleasure to moderate this panel discussion. We have this, exceptional group of all the panelists who brings together this expertise from computer vision and machine learning and robotics as well. So let me begin by having each panelist briefly introduce themselves, their background, and just interest in the physical AI or AI robotics. So maybe let's start with you, Jong. So just in 30 seconds, and could you introduce yourself and your background and your maybe interest in physical AI?
Thank you, Minsu. So my name is Jean Ponce. I'm professor of computer science at École Normale in Paris and New York University. I'm also the CEO of a startup called Hanra Lab, does image processing, and a co-founder and associate director for research for Prairie, which is an AI institute in Paris, which is a little bit related to the AI National Lab here, and I'm actually honored to be affiliated to the National AI Lab. I'm a computer vision person, but over the last 35 years now, I've dabbled in robotics, mostly in manipulation, mostly in geometric manipulation, and a bit in motion planning, and I'm still interested in it.
Thank you. Let's move on the table. So, Jongmin?
Yeah, hello, my name is Jongmin, and I'm an assistant professor at Yonsei University. So I'm basically a reinforcement learning algorithm researcher. So my primary research focus is about how we can develop the decision-making AI models in a principled way to make it safe and to make it robust and to make it data efficient. Yep, that's it. Thank you.
Hyunjung?
Hello. So to introduce myself, I think I start by saying that, well, I've been in industry for about 4 years at Samsung Advanced Institute of Technologies. There I work on kind of 3D visions with developing some sort of 3D sensors as well. And then I moved to Yonsei, and finally now at this KAIST AI, Kim Jae-chul's Graduate School of AI. And here, and then throughout my academic career, I've been focusing on more like the perceptions as well as the generative models, also the 3D visions. Yeah, so those are the topics that I'm interested in. Thank you.
Thank you. And Sungjoon?
Hello, my name is Sungjoon. I'm associate professor in Korea University. So whenever I go to robotic community, I say I do AI. Whenever I go to AI community, I do robotics. So apparently I do robotics because it's like an AI community over here. I started my career as a roboticist back in like 20 years ago, making a cleaning robot. On my PhD, I do mobile robot and manipulator. On my postdoc, I do humanoids and HRI. Now I do quadruped humanoids and manipulator. So I do different robots using both learning-based and traditional control-based method.
Thank you. Then Suha?
I'm Suha Kwak from POSTECH, not Korea University. And I'm computer vision researcher and...
Sorry for that.
No problem. I'm relatively new in physical AI, so recently I'm just interested in vision applications in robotics. For example, world models of robotics, improving robustness of robot perception systems, and cost-effective learning of robot foundation models. Thank you.
Yes, hello again. So I'm Ivan Laptev. I'm a professor at MBZUAI, which is a new university in Arab Emirates in Abu Dhabi. So where I'm since 2 years. Before that, I was in Paris in INRIA. And most of my career was doing computer vision from my PhD. I'm still interested in it, but I'm also much interested now in robotics because, well, as I mentioned just in my talk, so many proxy tasks which we've been doing for many years in computer vision, they are getting to the stage of being nearly solved, and but still understanding vision is important for robotics, embodied AI, and robotics is still in research. Even with lots and lots of GPU, we would still not know how to solve it. So I think this is an interesting problem to work on right now.
Thank you, Ivan. Yongsu?
Yeah. I'm Yonsei from POSTECH. I'm in charge of AI and robotics convergence R&D laboratories. POSTECH is a global company in steel and battery materials. We are actively leveraging AI and robotics to create value across our production lines. I'm going to share our experience in applying robotic applications to the manufacturing processes. Thank you.
Yeah, let's keep going. So thank you all for those introductions, and to set the stage for the round one discussion. So I'd like to invite Yong-Soo Kim from the POSTECH Holdings, the world best steel company, to give an opening statement for the whole panel. I mean, discussing maybe somehow the success and the challenges of the robotics applications in the steel making process. Yeah.
Thank you. We are applying AI and robots across the steel manufacturing processes to improve productivity and quality and safety. As you can see at our booth, AI now controls the blast furnace operations that once relied on human intuition. And in coating lines, AI predicts the coating thickness in real time and automatically adjusts the equipment. And using computer vision, AI detects steel surface defects and classify their types for corrections. Also, robots are taking over hazardous tasks. In Cocos oven, sealing robots replace manual labor, protecting workers from extreme heat and harmful gases. For regular inspection robots patrol areas with high temperature and dusty area, streaming live video and thermal data for remote monitoring. By applying robots to manufacturing processes, we've learned some important lessons. Steelmaking remains one of the most difficult industries to automate. In automotive or electronics manufacturing, many tasks are generally well structured and repeated. However, steel making involves large-scale, heavy, and unstructured processes. Tasks such as handling molten metal or inspecting massive equipment take place under extreme heat and constantly changing conditions. That challenges even the most advanced robots. The harsh environment demands heat-resistant and durable robotic systems that are complex and costly to develop. From a safety perspective, automation is essential not only to protect an aging workforce, but also to remove people from hazardous zones. However, simple installing robots isn't enough. The surrounding infrastructure and the processes must also evolve to support them. Additionally, domain knowledge is crucial. For example, before deploying mobile robots to perform facility inspections, we need a deep understanding of how humans actually perform those tasks. And these are some of the lessons we've learned so far. Thank you.
Thank you. So, yeah, thank you for the nice opening statement. And given the opening statement, so now we are about to discuss about these key questions from Young-Soo Kim. Yeah, I was trying to show this slide, but okay, it's not working for now. So we'll just talk about that. So basically, the background is like this. Basically, the traditional automation, as you know, it struggles in actually this very extreme manufacturing environment like steel making. So where tasks occur under very high heat and dust and constant variations. But so all we are actually expecting that physical AI, robots that can perceive and reason and act could offer a new path towards this autonomy in such a harsh and unstructured environment. So basically, this discussion question is like this. So in the building robots that perceive and reason and act effectively in such an unstructured industrial setting, like steel making, So what is the key challenge and how we can tackle it, this the practical issue in real-world robotics? So, yeah, once again, I'd like to start with John. Yeah, could you? Yeah.
Okay, so I have to confess I don't know much about the steel industry. I can imagine it must be pretty harsh environments. So I don't have any answer, but to me, I think it's nice to look at a lot of people doing a lot of tasks and learning a lot of stuff. But a factory remains factory. I think the robots you will have in there will always be the same robots. The layout of the factory will also be the same layout. It's not clear to me at all that the motion of people should be mimicked by robots that won't have the same kinematics, dynamics, motor behavior, and all that. So a lot of what we have heard about today and a lot of what people are working today is learning from robotics, and of course it's important. But I think there are other issues that are key. In semi-unstructured environments, like imagine a steel factory where things melting and all that, I still think that the planning part is very important, because I imagine things are changing, so you cannot just do a teleoperation things that you'll repeat forever. So you need to be able to generate robot motions in a nice manner. And I think planning actually, in my opinion, has been done in robotics in the last 25 years in a very naive way, where you have very greedy procedures that are not guaranteed to function. And it's complicated to make them work in a reliable way all the time as you need in a factory. The other thing that I think people should realize, I think industry people realize it, but I think vision people going to do robotics may not realize it as much, is that in robotics you have robots that interact with the physical environment. They touch stuff, they establish contact and lose contact all the time. You need able to reason about that, and you need to be able to reason about uncertainty. If you are going, I don't know if grasping is important in that field, but if you are going to grasp an object, you approach the object with your finger, you touch it, the object is going to move, and your plan is going to stop working. So you have, I think it's very, very important that, I mean, learning is great, but think about reasoning in the presence of physical contact and in the presence of uncertainty, so you have robust plans. I think that's important.
Thank you. So, Jongmin, do you have another opinion, or?
Yes. So I think that for the steel-making procedure in the industry, I think that the reinforcement learning can play a crucial role to automate it. But I think the one fundamental issue is that the well-founded reinforcement learning algorithms are based on very strict assumptions on the environment. So as a reinforcement learning person, when you write a research paper, we commonly assume the Markov assumption. The environment only depends on the current state and observation, or the environment itself is stationary. Based only on that assumption, we can derive some efficient algorithm to solve the problem. But in the case of the real-world scenario in the industry, I think that all of these kind of assumptions are significantly broken. So I think that if we have a internet-scale data, very much, if we have a large data set, then maybe we don't need any tailored reinforcement learning algorithm. But given that the industry data is very scarce, I think that we need some notion of the well-tailored decision-making algorithm, the reinforcement learning algorithm. So, for example, I think that maybe in the still-making procedure, so in the reinforcement learning, we commonly assume that even though we have some multiple decision variables, all the decision variables should be decided at every decision discrete time step. But in reality, some decision variables should decide at every, for example, 10 seconds, or some decision variables should be decided every 30 minutes, and so on. So yeah, I mean, there is some significant the gap between the idealized formulation and the real situation. So I think that in the algorithm perspective, we need to develop some algorithm that can fill the gap so that it can be robust to the noisy sensor input, and it can be generalizable to some unseen situations, and it can, yeah, and the some decision variables can not based on the some discrete time step and so on. So yeah, then if we incorporate this kind of real-world properties, then I think that we can do better in a data-efficient way.
Thank you, Jongmin. So, Hyunjung, you may have some opinion about this sort of robotic perception, I guess, in robustness in perception in robotic environment, I guess.
Yeah. I kind of think. So this is real environments, right? In the real factory. So perhaps if I was thinking, like, if I'm one who in charge of that huge projects, what would be the most important part? That I think the first thing would be the data, I guess. So the data itself, I'm very much working on this robust perceptions, and for these aspects, how we manage the training data, I think, is the first issue. So usually the most data handles the common situation, which has no issue at all. So therefore, just curating this data collectively, resulting this over-representing this common situation, but under-representing this very safety crucial or some situation which can be overlooked. But I think during this data curation, we got to be very careful that, although the most common scenarios are usually the case, but I think we have to somehow balance the data carefully so that we don't overlook such a crucial corner cases, because these corner cases can bring out a lot of issues in manufacturing scenario as well as safety, especially. I think the early stage of this, early stage of this autonomy usually comes semi-autonomous system, I guess, because humans and machines will work together. So under such a scenario, safety is really the crucial issue. So I think somehow in my lab, we also work on this. How can you actually take special care about this safety critical issue? So those are the things that we can also be careful and then being focused on too. Yeah.
Thank you, Hyunjung. So the next panel, Sungjoon. So you may have a lot to say. You promised to discuss in the final discussion.
Well, in robotics, we often partition the process into perception, planning, and action. In terms of those three topics, I think the perception is the most remaining problem right now. But having all the perception people said about the robustness, I don't have anything to say. Thank you.
Okay, Suha. So.
As a person studying perception part of robotics, I think I'm thinking about two different issues. One is environmental issues, like some extreme or adverse conditions for perception. And we may address that issue by adopting some existing machine learning algorithms like domain adaptation, generalization, or test time adaptation. But I think in physical AI, where almost all applications are safety critical and high stakes, we also have to be interested in developing sensors as well. For example, as a computer vision guy, I'm interested in developing camera systems as well. So, for example, if we can develop an optical system that can see through dust or fogs and even obstructions like dirt on the camera lens, then it will improve the reliability of the entire system significantly. And from the perspective of the task itself, unstructured tasks, I think, again, I'm new in this field, but I think it's important to understand and exploit the ability of robots to explore and manipulate the physical world, even in the perspective of perception. For example, robots are not, robots are active perception systems, so it can change its camera poses, and also it can touch or manipulate the worlds or exploit to see or to find better viewpoints to understand the current task and the scene. So by exploring such ability of robots, we may also improve the reliability and the success rate of robotic tasks, I think.
Thank you, Suha. So then, Ivan, so could you?
Yes, so as most of us, I'm not expert in the steel industry, unfortunately. But when I think about this problem, so one thing which comes to mind is that probably these industrial settings, the data is always going to be scarce. So we are not going to have much data. So, and from this, it leads that we probably need some digital twin or neural simulator or some sort of world model which will be able to predict us what will happen if we do this action or that action. And I think this actually, if we think of now neural simulator for a factory, this I think brings interesting questions and challenges because again, how do we train it? We don't have enough data, but this is an opportunity because we actually do have knowledge about physical processes which happens in a factory like thermodynamics or material science probably provide us with lots of prior knowledge. So I think the challenge in AI, because we still want to have AI to reason, to plan, to observe the scene, and so the challenge is to how do we make these components, AI components, which can perceive already images and understand text, how do we pair it with the physics knowledge which comes from thermodynamics, material science, and so on. So I think this is an interesting challenge which, if solving, I would guess, would bring us to some interesting solutions.
Yeah, thank you for all the opinions corresponding to Yonsei's opening statement. Yeah, before moving on, actually, if there is anyone who wants to respond to other opinions, other panels made, so if you can, yeah, Jean.
Yeah, I want to reiterate about safety because I've never been in a factory in my life, but if you're able to operate heavy machinery, you can kill somebody very easily because you need the physical strength to be able to operate the machinery. And again, you have physical constraints to take into account. You have the kinetic energy associated with the objects that you are carrying. You have all that stuff. And it's not like benchmarking on videos of people in rubber suits like we see always, etc. It's a real thing with real people, and it can be dangerous. And you want to be efficient. Efficient means you have to have robots who move fast, A robot who moves fast with heavy stuff is a very, very dangerous animal. So I think something to keep in mind.
Okay, any other opinion? Otherwise, actually, I'd like to raise one just issue to discuss. So basically, the Jong and Jongmin, so both of them actually made a point that basically there has been a actually large gap between this conventional formulation of robotic problems and this, actually practical and more like a realistic formulation of the robotic problems. So, what specific kind of maybe some entities or ingredient we have missed in this real-world robotic problems? So, if there is any opinion from the panelists, then I'd like to hear that or discussion. So, for example, Sungjoon, so you may have some, yeah, because you are the only actual, robotics guy in this panel, so you could be, yeah.
So yeah, so I think the simulation is always the problems. If you think about the advances in simulation, well, the core technology is still the same, and we still solve the rigid biodynamics. We still rely on a very approximated version of the quantic dynamics. We don't really handle deformable object in a full sophisticated way or in a fast speed. So I think the simulation itself, especially modeling the world with a lot of uncertainties, is the core problems here. So a lot of people think because the locomotion problem has been solved, people kind of tend to think that the manipulation task has been solved, but no, it is not. So we have to think about having a good simulation. We see a lot of simulations, for example, like Genesis, but they kind of rely on something called the material point method, followed by the finite element method, in which neither method relies a lot of tunings, very prone to, let's say, some sort of a segmentation fault-ish errors all the time. So yeah, I think there's no fundamental solution until we get some sort of a quantum simulation. So I think that will be my opinion.
And then what do you think about this future, world models? These days, everybody is talking about this world model, and they could somehow be used as a actually simulator in this robotic action generation. So, if
I mean, if you look up the world model at Cosmos, it's basically a video prediction model. But if you think about actually the in-hand manipulation, everything's been occluded by the robot hand. We should rely on the context sensors. Then there's no representation of the contact form because it's a three-dimensional space with infinite number of points. So basically, we don't have any ways to properly represent the real context that is happening in the real world in a very fast speed. So I think we need to have some sort of action-centric representation of the world for the world model, in which I don't have any answer to that.
John, you could
most simulators suck at physics. I mean, contact is very poorly modeled. Friction is horribly modeled. World model about predicting stuff is good, but we build a robot, so we know that if I apply a command to a robot, I vaguely know what it does, unless it's in contact with something else, and then all hell breaks loose. But at the same time, we know a lot. Again, I've never set foot in a factory. In a factory, I'm not going to take any possible robot. I will have the robots that I have in the factory. I don't need to observe the world of all the real robots, all the bipeds or the whatever. I don't need to look at 10 Airbnbs and collect data there because it's fun and it's diverse. It will be my factory. So if you believe that the key is collecting data within a constrained environment, even if depending on the application, things can be very wild, I think there are things that are feasible.
Yeah, it's a nice opinion. So, Ivan, you may want to respond.
Well, I already commented on world simulators. I think there is a potential. I agree that the current simulators, they don't perform well, but I think that's the challenge to make them much better than they can. In terms of, maybe I can comment also a bit on safety. So actually, we do have a demo, and where it's not steel industry, it's more energy industry, where actually atomic industry in Abu Dhabi, where people came to us and asked if we can do inspection, automatic inspection. I think that's one, could be also important area here for steel industry. So in atomic reactors, so there are places where you don't want to send people. Well, currently they send dogs which are controlled by people remotely, but then if the connection breaks, if something happens, the robots really need to be autonomous. I think similar probably applies to steel industry. There are cases where places where you don't want to send people, so autonomous robots can really be a change for this industry.
Yeah, thank you. Thank you for the nice opinions. Actually, I agree with that. Actually, time flies. So basically, thank you for rich discussion. So now we'd like to open the floor to the questions, if you have any. Maybe not. Yeah, no worries. We don't have enough time, so we can just move on to closing. So yeah, as we draw the discussion to a close, so I'd like to ask each panelist for just a final one sentence takeaway you'd like to the audience to remember. So Hyunjung, let's just start with you. Just fast forward.
Okay, so my message is, remember, we build the robots. The robots don't come like things that we don't know about. We know they are kinematics, we know they are dynamics, we know everything about them. We have good models of them. They are not perfect. And of course, you can try to estimate the difference between models that you have and reality. But we have the models. Remember this. Read the old robotics books. Be aware of what has happened. And it's not just. I think robotics is the challenge of AI, because this is where all the pieces of AI meet together, and it has to work in interaction with the physical world. But I think to be foolish just think of robotics as a black box deep learning problem where you acquire millions of hours of videos and you tweak a bunch of buttons and you use the knowledge that you have and then do the learning as well. So it was more than 30 seconds.
Okay, Jongmin?
Yeah, I think that for the physical AI to become more in our daily life, I think that we need to develop the fundamental, the generalizable and adaptable decision-making algorithms.
Okay, good. Hyunjung?
I think, yeah, the previous two researchers already said what I want to say. So I also think the robust perception is still the important issue. Yeah, and then someday, if we have a new sensors comes out, I think maybe the story changes. But unless we work with the humans and then try to understand the world as we do, I think we should make more robust perception. Okay, that's it.
Thank you. Sungjoon?
We see a lot of people say they're doing robotics nowadays. I hope more people to buy more robots for Korean companies. And hope to get out from the tabletop scenario to the somewhat real-world scenarios and do some experiments and hopefully discuss a lot about the real-world corner cases.
Suha?
I think vision researchers have a lot of opportunities in robotics field as well. And I think the key point is understanding the difference between the passive vision system and active vision system in classical computer vision and robotics, respectively. So I hope to investigate that direction, active vision with robotics, and yeah, I think many people here will have the chances to.
Thank you. Ivan?
Okay, I think we are missing representations which are both grounded in real data, in real sensory data, and which can also be grounded in physics, which we know from many years of prior research. I think creating this representation will push us in generally further and also towards applications in steel industry.
Okay, finally, Yongsu?
네, from an automation perspective, in the long term, we envision a phased transformation, starting with collaborative robots working alongside the human, and then gradually expanding to fully autonomous operations.
it feels like the central message from the panelists is, so we have to study and work harder in this reason. Okay, thank you again to all the panelists and to the audience for your attention and participation. So if you'd like to continue the conversation, so feel free to connect afterwards, maybe during the break or maybe online. So we now transition to the next session in, I think, 7 minutes. Yeah. So thank you for all the attention, and this is the end of the session 2. So please thank all the panelists and speakers here for the nice presentation and conversation and discussions.